All right. So this is a relatively short unit compared to the ones we have done previously. Okay? So there are not nearly as many major concepts in this unit, and none of the questions or problems that we've solved in this unit have been quite as intricate, let's say, as some of the ones we did in Unit 2. All right, where we had this force and that force, and they were all going different directions. We had to figure it all out. In this unit, it's been a lot more of Fc equals this force, and I just got to manipulate and solve. Okay, so the good news there is that you're not going to have a lot of questions that are going to have really, really long solutions. Okay, they're really basically one step, and then find out my answer. What's a little more difficult about this unit is that some of the contexts can be a little more confusing. So we have to make sure we read questions very carefully in this unit so we're actually solving for the right things. Okay? So when we started off this unit, the first day we just talked about uniform circular motion. Okay, the principles behind it. What does something have to exhibit in order to be considered moving with uniform circular motion? So if something is moving with uniform circular motion, then it is moving at a constant speed, but it is moving at, is not moving at a constant velocity, and that's because the direction is always changing. If the velocity is always changing, that means the object is undergoing, starts with A, acceleration. Where is it accelerating? Towards the center of the circle. What's the only reason something can accelerate?
Force.
Because there's a force, and the force and the acceleration are always in the same direction. So there has to be a centripetal or center-seeking force that is causing the object to accelerate towards the center of the circle, causing it to move at a constant speed but not at constant velocity. That's uniform circular motion. There will be a number of multiple choice questions asking about your understanding of that concept. They do not involve problem solving. Okay? They simply involve your understanding of the situation, forces involved, and things like that. Okay? So that was basically the first day. Right? So constant speed, changing velocity. That's delta with ing beside it. That means changing, by the way. Okay, velocity. Right? And we talked about centripetal acceleration being v squared over r. Okay? And that Fc is really just mass times acceleration. It's really just net force, but applied to something moving in a circle. So mass times centripetal acceleration. Okay? Right, so there could very easily be some multiple choice questions asking, like, which of the following is something is a characteristic of an object moving with uniform circular motion, and you would have to pick which ones. All right, then we talked about our kind of first example of uniform circular motion, and that was an unbanked curve. Okay, what holds you in an unbanked curve is the force of friction. Right, so anytime you have something negotiating an unbanked corner, okay, FF equals FC, okay, because friction provides the centripetal force that keeps you from sliding out of the corner. Okay, so we have things like mu times mg. So this is the force of friction right here, okay, mu mg, okay, and we're using mg here because normal force and the force of gravity on a unbanked surface are not zero, no, they're the same. Right now this desk, okay, the force of gravity is pulling it down into the floor, and the floor is pushing up on it with the same amount of force, which is why it doesn't go anywhere. Okay, so for an unbanked curve, that's what we're looking at. FF equals FC. All right, and then we talked about banked curves. So now a banked curve doesn't have to rely on friction. So what we do is we take the surface and we bank it a little bit. And now that surface provides a normal force, or gives a normal force that is directed straight out from the surface. Its vertical component offsets gravity, and its horizontal component is directed towards the center and acts as a centripetal force. Okay? And so that's where we arrived at the bank curve formula from. I'm not going to go through the derivation again because you guys don't need to know it. Okay, but we said that the tan of theta equals v squared over r times g. Okay, for an for a banked corner. right? And that could allow us to calculate things like if a car wants to negotiate a bank curve at 20 meters per second and the radius is 500 meters, what's the angle the curve is banked at? Or what's the maximum safe speed for a curve that has a radius of 200 meters and a bank angle of 20 degrees, or whatever, okay? You're manipulating that formula and you're solving for one of the variables in it. All right, could there be some multiple choice questions about bank curves? Yes, there could be, as long as you understand how they work. Banking the curve brings in other forces that we can use that have components directed towards the center of the circle, acting as centripetal forces. Okay? What was the main reason for building bank curves? Nope.
Safety.
Safety. Okay? If I build a bank curve correctly, do I need to rely on friction at all? No. Now, since there's really never going to be a situation where there is no friction, banking a curve makes it much safer than an unbanked curve, because there'll always be some amount of friction and the angle of bank to help you stay in it. So they essentially make a corner that you can take at a recommended speed that will be safe regardless of the conditions of the road. That's kind of important here in Canada, where road conditions can vary greatly from 1 minute to the next, literally. Okay? Or like when we went to West End, you know, as soon as we got across the river, the Bow River, it was suddenly like sunny and clear. Okay, same when we came home. So, okay, these make roads much safer. All right, questions on bank curves? Okay. Then we talked about artificial gravity. Okay, how do you generate artificial gravity?
Spin.
Right, you make a spinning drum spin. Okay, or you make a drum spin or a cylinder spin and you're on the inside of it. Okay, it works because which way do you want to go?
Out.
Okay, out of it in a straight line, tangent to the circle. What does the inside of the drum do?
Curve.
Yeah, okay, it curves. It pushes against your feet. It makes you feel like you're not going to leave it. Okay, so it gives you the impression of having weight. So your inertia wants you to do this, that is follow this arrow here, but you push into the inside of the drum and the drum pushes back, and as long as I make the drum spin fast enough, I will feel a force equal to my earth weight, or more, or less, depending on how fast I make the drum spin or what the radius of the drum is. Okay? In the end, I probably want the centripetal force to feel like my weight. Okay, so Fc is going to typically equal Fg in a artificial gravity situation, unless it was to say something like you want it to feel like 1/2 of Earth's gravity. Well, then that would change this formula to say that Fc equals okay, if I want to feel half my weight, then I put in half my weight, okay, or 1.5 times the weight, then I put in 1.5 Fg. Okay, I just manipulate for whatever situation it calls for. All right, questions on artificial gravity? All right, then we talked about vertical circular motion, which is not uniform. Okay, all the other things we talked about, bank curves, unbanked curves, and artificial gravity are all uniform circular motion because the speed of the object in the circle does not change. For vertical circular motion, it does change. Okay, it moves fastest where? Bottom of the circle, slowest at the top. Okay, if I'm going to actually navigate the entire circle, is there a minimum speed I have to achieve? Where does that minimum speed most important? At the top, right? If I don't go fast enough, I fall out of the circle like Homer did in the Ball of Death. Okay, so we want to make sure that we have that minimum speed. The key thing with vertical circular motion is this. Fc is the net force. It is the forces into the circle minus the forces out of the circle. All right, so if you encounter a problem on the exam and it's talking about a vertical circle, okay, you know automatically Fc is forces in minus forces out. The most difficult part of that is deciding which forces are which. Okay, so we'll quickly review the 3 situations we talked about in terms of a vertical circle. All right, if I am going over the top of a vertical circle, as in this situation here, gravity wants to pull me down towards the center of the circle, or in. And normal force pushes out, unless I do what? Unless I go fast enough that I lose contact or don't touch the surface of the circle, in which case I would feel weightless. Okay, so the condition of apparent weightlessness is most commonly produced while going over the top of the vertical circle. Okay, Fg is the force in, normal force is the force out, unless you are apparently weightless, and then you only have Fg, because Fn would be 0. All right, if I am at the top on the inside, this is where I would have that minimum speed. Okay? If I'm going just fast enough to stay in the circle, do I push on the circle at all? No. So then there would only be a force of gravity acting in and not a normal force. Okay? I only have a normal force if I'm going faster than the minimum speed. Since none of you got to ride the mind bender because it was shut down and they didn't tell us about that, which sucked. Okay? You never got to feel this, but as you go through those loops, you actually feel crushed at both the top and the bottom because you're going way faster than the minimum speed necessary to negotiate the loop. Okay? So, if I'm going faster than the minimum speed, there is an Fn. If I'm going at the minimum speed, there's no Fn. If I'm going slower than the minimum speed, you don't have to worry about anything because I'm not moving in a circle. Okay? I'm just following. Everybody follow there. Okay. And then the last situation has to do with the bottom on the inside of the vertical circle. Okay? This is where I would feel the heaviest. Okay? Because not only does my inertia cause me to push on the circle, but so does the force of gravity. Okay? So the circle has to push hardest when I'm at the bottom, which makes me feel the heaviest at the bottom. My apparent weight would be the greatest at the bottom of the circle, and it is, of course, acting towards the center. Okay? So in this case, Fn minus Fg. Okay? Forces in minus forces out. All right, and we had a couple of questions where they said, what would the radius of the circle be for someone to feel 3 times their normal weight? Right, and we said, in a situation like that, Fc would be forces in, normal force, minus forces out, gravity. But since we feel 3 times heavier than normal, we substitute in what 3 times normal looks like. 3 mg minus mg. Okay, and then we solve from there. Okay, question could you? Okay, should you expect to see a vertical circular motion problem on your test?
Yes.
Yes. Okay. All right, and then for number 6, okay, we've got universal gravitation. Okay, so this, the 6th thing we went over in this is Newton's universal law of gravitation. There are several multiple choice questions asking about your understanding of this. And the most important thing you need to understand about Newton's universal law of gravitation, okay, which looks like this, is that this force of gravity is not a force of one object on the other. It is mutual. Okay? They both pull on each other equally. Okay? The force of gravity is a mutual attractive force between 2 objects. Okay? A mutual attractive force. So, the Earth and the apple. Okay? We're talking about Newton's experiment here. Okay? The Earth and the apple are equally attracted to each other. Okay? The Earth is just as attracted to the apple as the apple is to the Earth. Okay? And because the Earth is so much bigger, do we notice it? No. Okay. All right. The other thing to remember is, according to this formula, okay, the effect of radius is exponential. So if I double the distance between 2 objects, the force of gravity between them will be divided by 4. Okay, it's an exponential relationship. The farther apart you get, you will be exponentially less attracted to the other object. Okay? And again, don't try to apply that to anything other than gravity. It doesn't mean long distance relationships don't work because you become exponentially less attracted to someone because they're not around. There's lots of other reasons they don't work. Okay. Just okay, good. Somebody chuckled. I was starting to feel really bad there. Okay. Now, we did a couple of questions in class about net gravitational force to do with universal gravitation. Okay, the one we did in class said, here's the sun, here's the earth, and here's the moon. Okay, find the net gravitational force on the earth due to the sun and moon. Okay, what are the two forces pulling on the earth? Right, the force of gravity between the earth and the sun, and the force of gravity between the earth and the moon. Can I find the net force between them? Yeah, net force is the vector sum of all forces. Okay, probably expect something like that. Okay, where you're asked to find net force on there. Okay. Oh, and then I drew it there. All right. Now, satellite motion. To solve any satellite motion question, what provides my centripetal force? Gravity. All right. So we're saying mv squared over r equals big G times mass 1 times mass 2 over r squared. What mass always cancels in this? The little one. Right. The orbiting body, the satellite, always cancels. Okay. So they can all be solved that way. Things we need to remember: radius needs to be in meters, mass needs to be in kilograms, and if I get a question that gives me period needs to be in seconds. Okay, that's kind of the trick. Should you expect one where I give you the type of information where you would have to substitute, like on the quiz today?
Yes.
Yes. Okay, I would expect that type if I was you. I'm not you, but I'd still expect it. Okay. Remember, there's a couple of key words that could be used to trick you. That would be if the question asks you to calculate height or how far above the surface or the altitude. Okay, that means you will have to use the Earth's radius as well. Or it gives you the height above the surface or the altitude, and you would have to add on the Earth's orbital radius onto that number. Because remember, radius is the distance from the center of one object to the center of the other. Okay, so keep that in mind. Okay, those are trick words that could come up in a problem on the test. Right, like we said, FC equals FG. Okay, it could be possible that you have to substitute this in for V. If you have to do that, then you have to square everything in it and plug it into the formula like so. All right, so our V would disappear. 2 squared is 4, pi squared is pi squared. We have an r squared on the top and an r on the bottom that cancel, leaving us with 1 r on the top and t squared on the bottom. Okay, so important that you can perform that substitution on the fly. Okay. Incidentally, just like all the other tests, you will not be allowed to have your formula sheet. You will get the one that I put on the front of the test. That means that formula will not be on there. Okay? And you will have to come up with it on your own. All right, and then lastly, we talked about gravitational field strength, which simply calculates acceleration due to gravity at any given point. Okay? It is not a difficult formula to use. It is never set equal to anything else. It is simply a formula for its own sake. The difficulty lies in identifying whether or not the question is asking you to calculate gravitational field strength or giving you gravitational field strength. And you will know that because I will boldface, italicize, and underline the words gravitational field strength. So be on the lookout for that. That is not the same thing as the force of gravity. Don't make that mistake, please. Okay? So remember that gravitational field strength is your acceleration due to gravity at a certain point, not the force of gravity at a certain point. Okay? All right, and then we also talked about Kepler. Okay, it's possible that I could make a mistake and put a question on a test that could be solved more than one way. It would be a satellite question, obviously, but if I give you the right information, it's possible you could also solve it using Kepler's law of periods. Or you could just solve them all using FC equals FG. Okay, because that works for all satellite motion problems. Okay, this only works if I give you exactly the right information. Okay, should you also know about Kepler's other laws? Yes, he has 3. Okay, the law of elliptical orbits, the law of equal areas, and the law of periods. Okay, that sets up pretty nicely for a multiple choice question, like which of the following is not one of Kepler's laws. Okay, so I would be familiar with his laws just in case you get a question like that. All right, and I think that's it. That's all the stuff in this unit. So we're looking at 15 multiple choice, 8 written. Actually, I think I'm going to change that. Hang on, let me double check here. I know I changed some things. Yeah, 8 written response. Okay. So 15 multiple choice, and like I said, most of them are just understanding type questions. There's basically there are actually no multiple choice questions that involve you doing a calculation. There are some you could do a calculation for, but if you really understand the concepts, you don't have to. Okay, so there's no need for any calculating in the multiple choice. Right? In the written response, okay, then we're looking at basically the things that are on there. Okay, the 8 things that are on there. Uniform circular motion, that can be curved. The 2 types of curves. Okay, vertical circular motion, satellite motion, universal gravitation, artificial gravity. Okay, all that kind of stuff. The key things that are up there are the things that are going to be in the written response. Right. So this is the shortest test that you have written for me. Right. Only 15 multiple choice, and there's only 33 marks in the written, so it's out of 48. I think your next shortest one was like 60. Okay. So this test is shorter than the others. Do not take it lightly, however. Okay? You should do well on this test. You should do better on this test than you did on the first 2. Okay? But don't take that to mean, Coderre said this test is easy, so I don't have to study. I'm saying this test is an opportunity to improve your mark in your exam section of your mark significantly if you come in prepared. Right? So if you prepare well for this test, okay, you know what kind of questions are going to be on it, then you should be okay. But if you just say, there's not that much on this test, I'll do fine, you're wrong. Okay? And I don't want you to be wrong. So do it right. Study hard for it. Okay? All right. Are there any things you want me to go over in more detail or show you here in terms of review from this unit?
Can we do a question on a banked curve?
Banked curve. Okay. How about this one? It's like I read your mind. That's scary, I didn't read your mind. Okay. All right. So, what speed can a 16-degree banked curve with a radius of 70 meters be negotiated? All right. So our givens in this question are theta, 16 degrees, radius, 70 meters, and we are looking for speed. All right. All banked curves are governed by this formula. The tan of theta equals v squared over r times g. Okay. This question wants me to solve for v. So what do I do with the r and the g? Right. Multiply them over to the other side. So I'm going to have the tan of theta times r times g equals v if I square root it. All right. So plug in my numbers here. So we'll have the tan of 16 times 70 meters times 9.81. Oops. Still not what I want. All right, so I got to square root that. All right, so we're looking at a speed of 14 meters per second for that corner. Okay, so a bank curve is either going to ask you for theta, it's going to ask you for v, or it's going to ask you for r. Okay, it will give you the other two, or at least the ability to calculate the other two. All right, what else?
Like, is it gonna ask if it's gonna, if like, if I'm gonna ask you a question about a car, like sliding in?
You had a quiz like that, right, where I said, is the car going to slide in, slide out, which is basically the same question. I would just say the car is moving at 20 meters per second. So you just have to recognize that 20 meters per second is faster than this corner can be negotiated, so it would slide out, right? If it was going 12 meters per second, it would slide in.
When you divide by 10, does it become the inverse 10?
No.
No.
No. If I'm looking for theta, I bring tan over to this side, I invert it.
Okay.
Okay, that's when it becomes inverse tan. If I'm moving all of like tan of theta, it doesn't become inverse. Right? So if I'm manipulating for, well actually there's no case where I would move tan of theta, but in this case here I brought other things over, that didn't invert it.
Yeah.
Right? So if I was looking for r, let's say, okay, then I would bring r over here and divide the tan of theta over there. I'm not inverting the tan, I'm dividing by the tan of this number. Does that make sense?
But if you're looking for theta,
Then you use inverse, right?
Okay.
Okay, what else?
Can you do an artificial gravity question?
Okay. Wow, astronaut. Can't even spell astronaut today.
Say spaceman.
I'm gonna say spaceman. Spaceman. Okay. Feel on a space station. I have no idea. I hope this isn't like going to crush the astronaut. I'm just making up numbers. Okay. So we've got a spaceman on a space station that has a radius of 60 meters, spinning at 40 meters per second, and I want to figure out how many times their normal weight they're going to feel. Okay. So for artificial gravity, Fc equals Fg. Okay. So that's going to mean mv squared over r equals mg. Okay, which one of those variables will tell me or allow me to figure out how many times heavier than normal they feel? Gravity. Yeah. If I can calculate the acceleration due to gravity for this space station, how much it produces, I can use that divided by 9.81 to figure out how many times greater than normal they feel. Right? I'm solving for g. I'm not saying g is 9.81 here. It's something else. Okay? I don't know what it is. All right, so I'm going to solve for g by canceling the m's and plugging in my numbers. Okay, so I'm going to have v squared over r. It's going to be big. Big. Oh, it's only 2.7. They actually feel lighter? Oh. Okay, well, let's make it 140 then. Now they'll feel heavier, really heavy.
When do we, how do you know the difference to use FC is equal to the Newton one rather than this one?
Because you use the Newton one if you're dealing with a situation where there'd be no way to have little g. For this space station, there wouldn't. The people would be on it. I'd know how they felt. Yeah?
But if it's like a planet, you'd use the Newton one?
Right, because that's not artificial gravity. That's real gravity.
Oh, yeah.
Okay, so if I do that, then I'm going to have 140 squared, okay, divided by 60. All right, oh yeah, that's really bad. This is not a fun space station. You would be a puddle of goo, okay, undergoing 33 Gs. Yeah. That would literally snap your bones. You would be a puddle, okay? You're not gonna see. All right, this is what happens when you just pick numbers randomly out of your head. It's either too light or too heavy or whatever. Okay, what else?
Vertical circular motion is
Okay, what in particular? Because there's lots of different situations.
a minimum speed.
A minimum speed one, okay. Okay, so I've got a vertical circle that has a radius of 25 meters, and I want to figure out how fast do I have to move in order to stay in that circle. Where does the minimum speed occur in a vertical circle? On the,
Bottom,
no, top on the
side.
inside. Okay, I don't require a minimum speed to drive over a hill. Okay, I'm not going to fall through the hill. Okay, but I could fall into the hill if I'm on the inside of it. All right, so at the minimum speed, am I pushing on the track? So then my only force is gravity, right? So at the top of the circle, guys, remember, Fc equals forces in, gravity, minus forces out. There aren't any. Okay? There are no forces out at the minimum speed, or on the top on the inside. Okay? So I'm going to have mv squared over r equals m times g. And I'm just solving for what here? Well, not v squared, v. Right? I want to find v. So I'm going to multiply both sides by r. M is going to cancel. Square root of GER. Okay? So v will be the square root of 9.81 times 25. All right? 16 meters per second. Okay, so minimum speed is actually one of the easiest types of vertical circular motion questions. Right, Gavin? Okay, what else, guys?
Can we do one where Fn is really big?
Fn is really big, so on the bottom?
Yeah.
Okay. Okay, so we have a vertical loop. We're at the bottom of it on the inside. Okay, it's got a radius of 16 meters, and we're moving at 35 meters per second. We're looking for the apparent weight. What force is apparent weight? Normal force. That's something you'll definitely need to remember. Okay, so normal force is acting in, gravity is acting out in this situation. Fc equals forces in minus forces out for all vertical circles. Okay, so we're going to have mv squared over r equals Fn minus mg. I'm trying to find apparent weight, so what do I have to do with mg? No, I don't want to cancel it. I want to add it over to the other side, right? I'm subtracting it right now. Okay, so I'm going to have mv squared over r plus mg equals Fn. This is why Fn is so big at the bottom of a circle. Okay, so that'll be 65 times 35 squared divided by 16. So that's our speed and that's our radius, plus 65 times 9.81. Okay, so that's their apparent weight, 5,614 newtons. That's a lot. That's 8.8 Gs. Okay, you probably black out. Okay. Lisa?
When you do Kepler's law,
Okay. Okay, looking for the orbital period of a comet orbiting the sun at a distance of 3.2 times 10 to the 14 meters. So what did I give you? I gave you orbital radius. I gave you the radius of the comet's orbit. Okay, so that'll be 3.2 times 10 to the 14. If I'm going to use Kepler, I need one more object that orbits the sun. Earth. Okay, so I'm going to say that the period of the Earth squared over the radius of Earth's orbit cubed equals the period of the comet's orbit squared over the radius of the comet's orbit cubed. Now, something I saw people doing on their circular motion assignments, okay, that they need to watch out for. Radius of the Earth's orbit, not the radius of the Earth. I saw a number of people who were plugging in 6.37 times 10 to the 6 when they were using this formula. That's the radius of the Earth. You are going to get ridiculous answers if you do that, because you're essentially saying that Earth is orbiting the sun from inside the sun. Okay? Follow me there? You got to use the radius of the Earth's orbit, which is 1.5 times 10 to the 11 meters. All right, I'm trying to find the period of the comet, so I'm solving for TC. I'm going to move RC cubed over here, and then I'm going to square root all of this. Okay, so the period of the comet will be the square root of 3.2 times 10 to the 14 cubed times 1, period of the Earth in years, okay, divided by the radius of the Earth's orbit, but I have to match it. It's got to be in meters, so 1.5 times 10 to the 11 cubed. Okay, so that's a lot. 98,000 years. I probably messed something up in the numbers, but I picked them out of my head. That's probably why. Okay, 10 to the 14 is a long, long way away. Okay, that's like several hundred times further than Neptune. I probably shouldn't pick such a big number. But yes, it would take 98,000 years at that distance, okay, to orbit the sun. So if you were lucky enough to see that, no one else would ever see it. Okay. All right, any other ones? Okay, well, you have the unit exam review package I posted last week on Google Classroom. I would suggest that that's probably a good thing to be working on right now. Okay, there's some suggestions and some definitions and review stuff in here. Okay, and then there are some formulas, and then there are some review problems with the answers in bold and brackets. Okay, that you can check out if you want. I'll just leave the review problems up.